Controlling and control of a quadcopter.
Group 20G26, Kalisha Ratalal and Christian van der Merwe.
Quadcopter control is essential to ensure safe operational environments for both the craft and people. An autonomous control system is developed for a constructed and modeled quadcopter.
This diagram depicts the electronic system integration of the proposed quadcopter construction. It includes a power distribution segment that interfaces with the ESCs, which subsequently interface with their respective motors. It also supplies the IMU and microprocessor via the power modulator. The figure on the right depicts the direction of rotation of each motor. This allows the Euler angles of the craft to be controlled using a PWM signal applied to the ESCs, which vary the motor RPM.
This figure depicts the arrangement of these components.
The Newton-Euler mathematical model of the system is described using a special Euclidean space of order 3. It assimilates the equations of rotational and translational motion, as well as the position and orientation dynamics of the craft. This is accomplished using the rotation matrix R theta, which is obtained by consecutive and non-commutative rotations about the three perpendicular Euler fixed body axes. Because the craft is structurally symmetrical, the inertia matrix can be described as diagonal.
This flowchart depicts the system logic and magnifies the controller algorithm, which employs the three Euler angles directly and uses references of zero for stable hover. This employs three independent PID controllers that convert the angles to controllable torque, which is then passed through a torque to thrust conversion matrix. This generates a usable PWM signal through the use of an experimentally determined relationship.
The angular velocity controller incorporates components of the aforementioned Euler angle PID algorithm, which only activates when the measured angle is outside a certain bound. Within this range, the angular velocity controller is active. It is parameterized by previous and current Euler angle measurements and loop iteration time. This determines the angular velocity. Similarly, this controller applies tuned gains to obtain a torque matrix. The subsequent logic is consistent with the aforementioned controller.
Testing is executed with the craft in a secured cage for safety precautions. The stabilization control algorithms are tested within a consistent and controlled environment using a harness, which still permits craft mobility to emulate hover. The craft is lifted via one arm to incremental angles and subsequently dropped to analyze the functionality and effectiveness of the controllers.
The videos present the craft being dropped from a 60-degree angle imposed by lifting motor 3. The raw angle PID controller exhibits a shorter settling time to within a ±2-degree bound around the reference angle. Moreover, it showcases a smaller percentage overshoot. The angular velocity controller displays noisier characteristics and a greater degree of oscillations, particularly with regards to roll and yaw. This leads to the conclusion that the raw Euler angle PID control system exhibits more desirable dynamic characteristics. Impermissible oscillations may result in nonlinear impacts on the complex system, which can amplify quadcopter destabilization during flight.